going to consider now a body which moves in the x direction only, being subjected to a conservative force. And the example we're going to use is a glider attached to a spring. So we have here a glider of mass m moving along in the x direction on an air track. And we assume that the glider is given an initial push to set it in motion. After it has been set in motion, it will oscillate back and forth along the track. And as it is a linear air track, the friction will be minimal, so we can ignore it. When the glider is moving to the right, the spring exerts a restoring force to the left, Fx, which is equal to minus Kx on the glider. The potential energy function for the system we know is Ux is equal to a half Kx squared. The graph which has appeared on the screen now shows the plot of Ux as a function of x. Since we're neglecting friction, the spring force is effectively the only horizontal force acting on the glider, and it is a conservative force. Therefore, the total mechanical energy of the system will remain constant. If the total mechanical energy of the system is represented by E, then it is equal to K plus U, the kinetic energy plus the potential energy. If the initial push that we give the glider gives it a certain amount of energy E, and this is constant, we can represent this on the graph by a horizontal straight line, as shown here. The vertical distance between the plots of U and E at any point gives us the kinetic energy K of the glider at that point. Note that the kinetic energy is a maximum at x equals 0, the equilibrium position, and 0 where the two graphs cross. The potential energy can never be greater than the total mechanical energy, so where the U and E graphs cross defines the maximum amplitude of the oscillation. At each point, the force Fx on the glider is given by minus du by dx. In other words, the negative of the gradient of the graph at that point. So at x equals 0, the gradient of the graph is 0, so du by dx is 0. Therefore, the force is equal to 0, so this is an equilibrium position. When x is greater than 0, du by dx is positive, the gradient is positive, so Fx, the force, is negative. In other words, it's directed along the negative x-axis, or x direction, towards the equilibrium position. When x is less than 0, du by dx is negative, so Fx is positive. In other words, acting along the positive x direction towards the equilibrium position. Therefore, Fx is a restoring force, trying to return the glider to the equilibrium position all the time. We say that x equals 0 is a stable equilibrium position. It's rather analogous to the situation where a marble is rolling backwards and forwards up and down the sides of a salad bowl. Generally, any minimum on a potential energy curve is a position of stable equilibrium.